All right, we're in Unit 9, Application of Thermodynamics. This really is about delta G. Let's get to the questions. Here we go. All right, number one. Okay, I really didn't like this question because there's a couple things that I don't like about it, and I'll show you. Okay, for the reaction represented above at 25 degrees Celsius, what are the signs at delta H, delta S, and delta G? All right, so let's take a look at delta S. Now, you have 3 moles of gas, right, on this side, and you have 2 moles of gas on this side. So did it get more orderly or less orderly? It got more, did it have more disorder or less disorder? It has less disorder, right? I always tell you to think about the gases like they're grandkids, you know, kindergartners running around. There's 3 kindergartners now, there's only 2 kindergartners. It's gonna be more orderly or less disorderly. So delta S is gonna be negative. So right now we're between these two. Here we go. All right, for the reaction represented above, what are the signs of delta H? Okay, so, well, delta H here, you got to do bonds broken minus bonds formed, and because they didn't give you the delta H here. And you might know, you might have memorized this, but I haven't, so what the heck? All right, you see that H is, let's draw this. Let's draw this. You have H2. You have 2 H2s, you have 1 O2, and then you have 2 H2Os. These 2 H2Os now, okay, I really don't like doing it this way. You have a negative 1, 2, 3 bonds, and on this side you have 1, 2, 3, 4 bonds. I don't know what those are, but you remember there is a delta H calculated by using bonds broken minus bonds formed. And without knowing these values, well, there are 3 bonds being broken to 4 bonds being broken, which is the best that I could give you right now. I don't know how else you would be able to do this question. Actually, there is a way, and I'll get into that. Well, if there's 3 bonds broken and 4 bonds formed, then it would be overall, there would be more bonds broken than formed, so this delta H would be negative, okay? So right now we are at this point. Delta H is negative, delta H is negative, okay? Now the other way to think about this is you got to remember that the formations of bonds are exothermic, right? So when bonds are being formed, that is exo. When bonds are being broken, that is endo. So if you have more bonds formed than bonds broken, I guess you could say overall you'd be exo. I really don't like thinking like that. It's a little bit too up in the air. Now, I'm not a numbers guy. I'm not someone that will argue that you got to do the numbers. However, this feels a little bit too, I don't know, there's not enough calculation here. And then this is the part where I really don't like. Okay, well, if you don't know your delta H and you don't know your delta S, like in terms of number, right? Then how are you supposed to know your delta G? Well, if you remember, when you have this formula, and this is delta G is equal to delta H minus T delta S, if you have a negative like we do here, it all depends on the temperature, okay? If the temperature is small, okay, if you have a small temperature, then you could say this guy gets canceled out and this guy wins. Okay? If you have a negative, but this time your temperature is super big, right? Then your enthalpy gets canceled out and this guy wins. In this case, the question said we were at 25 degrees Celsius, which is generally considered a pretty low temperature. So this scenario wins down here, right? Which means it would be negative, negative, negative. Okay, the correct answer is D. I would say that question is I don't like how it's being solved. Like there's a little bit too much open range there. And without knowing like what the numbers are, like that is a bad way to start a packet. But yeah, when I did this last night, I was going like, ugh, I don't like this question. All right, let's go to number 2. Okay, this will bring up an idea that I really want to talk about, so this is good. All right, you have two H2s plus an O2 yields two H2Os. When H2O and O2 are mixed together in a rigid vessel at 25 degrees Celsius, no reaction occurs. When a mixture is sparked, however, okay, sparked, what the heck does that mean? However, the reaction reacts vigorously according to the equation above, releasing heat. Which of the following statements correctly explains why the spark is needed for the reaction? Why is the spark needed? Well, this must be, okay, it says that, reactions can be spontaneous. They just sometimes have a large activation energy, and that's why we need to add energy for them. The reaction has a large activation energy at 25 degrees Celsius, okay? I want to make sure that you guys understand, just because a reaction is spontaneous, it doesn't mean it happens right away. Like I said before, water on iron is a spontaneous reaction. It's just, it takes a long time, okay? So our ideas of spontaneity can't be that it happens fast, it happens fast. That's not true. It just happens without help. Here in this case, this reaction has a large activation energy. So when we add that activation energy, the reaction will go. All right, number 3. A cube of ice is added to some hot water in a rigid insulated container, which is then sealed. There is no heat exchange with the surroundings. What has happened to the total energy and the entropy when the system reaches equilibrium? All right, it wrote something. Okay, it wrote 2 things. It said a cube of ice is added to some hot water in a rigid insulated container. Okay, let's not even go that far. Let's just say a cube of ice added to hot water. Most of you have put a cube of ice in hot water before. What happens to the ice and the hot water? Well, the ice melts. Yes? The solid turns into a liquid. So you have grandparents becoming parents, right? Grandparents. I always say, solids are like grandparents. Okay, liquids are like parents. Okay, so you have grandparents becoming parents. Okay, so you have more disorder. Okay, more disorder. Okay, that means your entropy, you went from solid to liquid, your entropy has increased. Okay, that's the first part. So we're now dealing with C or D only. All right, which is then sealed. Okay, it's been sealed. There is no heat exchange with the surroundings. When it says there's no heat exchange with the surroundings, that means all the energy is kept constant. That's that. Okay? So the correct answer is here. That's the law of conservation of energy. Okay? You just got to read the question to find out specific details that are going to pertain to either energy or entropy. And to say that the energy would decrease, you would have to say that the energy of it's not asking about the energy of the ice alone. It's asking the total energy, right? And the total entropy of the system. So even though maybe the hot water lost a little bit of energy, the ice water gained a lot of energy, so that it remained constant. All right, number 4. Finally, we got kind of like a math problem here, but if you actually look at the answer choices, you don't actually have to solve them, you just need to be able to set it up correctly. All right, so let's do it. All right, so a reaction between SO2 and O2 is present. Okay, so what we're going to do is this. You got to remember that delta S is equal to S product minus S reactant. Your product is 2 times SO3, which is 257, minus 2 times your SO2, which we don't know what that is, plus 1 times 205. And that has to equal the overall delta S over here, has to equal negative 187. Okay. Look, where did I get these 2's from? Right here and here. They are from the coefficients right here and there. Okay. Now, remember, I just did something that I really shouldn't have done. Remember, right here, you have to get, this is all of the reactants. I should have put that in parentheses. So the entropy of the reactants has to be in parentheses so that you make sure that you're subtracting both of the reactants. Okay. That correct answer, let's take a look. That answer is C. you're gonna end up just manipulating all of this stuff to find your x. It's trying to get x by itself, right? Okay, now whenever the test gives you standard reduction potentials, these are reduction potentials. In other words, this is a reduction reaction. This is a reduction reaction. It doesn't mean that they're both reducing. It means one of them is oxidizing. We just got to figure out which one. Now, let's say this. The table above provides a half reactions and standard potentials needed to determine if an Al air fuel can be constructed. Which of the following equations best supports the possibility of obtaining electrical energy from such a cell? Okay, so if you have, all right, okay. Okay, if we want to obtain electrical energy, that means this thing has to produce energy, not require energy. So this means, this phrase right there means it's galvanic. Look, electrolytic cells, we have to put energy into them, right, to make them work. This one, we are obtaining electrical energy. We're getting electrical energy, meaning this is happening spontaneously. For this to happen spontaneously, that means your delta G has to be negative. And if you remember, your delta G is equal to negative NFE. And if you need to watch my video on the galvanic or delta G review, do that. Okay, if this is a positive number and this is a positive number, N and F are a positive number times a negative number, okay? So overall, this thing that I just highlighted in red is absolutely going to be negative. Negative, positive, positive, right? Negative, positive, positive is, if you have a negative times a positive, you're going to get a negative. That means if you want delta G to be negative as well, that means E cell has to be positive, right? So E cat minus E an. E cell has to be positive, and E cell has to be E cat minus E an. Now, if this has to be positive, okay, let's do this with these two standard reduction potentials. We're going to do E cat. Okay, we're going to do this. We're going to treat this like the cathode. Negative 2.31 minus 0.40. Or you could get 0.40 minus negative 2.31. Okay, I'm not going to calculate that number. It's a waste of time. But you can see that if I do this version of it, I will end up with a negative number. That's not what I want. If I do this version of it, yeah, I will end up with a positive number. And that is what I want. I want a positive E cell. I want a positive, okay, so think of the logic. Work backwards with me. If I have a positive E cell, yes, then I can put that positive into this E, and then I will have a negative times a positive times a positive times a positive. Yes? And this will be negative, giving me a delta G that is negative that will be spontaneous. So in other words, this map of blue that I just went on, this is the correct situation. It means that you have that, okay, so remember, this is how I calculated E cell. E cell is equal to E cat minus E an, okay? So this is wrong, the blue is right, meaning this guy is our cathode, this guy is our anode, right? Anode, cathode. Meaning this guy is rigging and this guy is oxidizing. Anode, N-ox, red cat, okay? Now, so the first thing that I know is that it has to be, it can't be C or D because those are going to give me negative E cell values, so that's going to give me the wrong delta G. Now, if you look at these numbers, how is delta G calculated? Okay, now remember, we've canceled out this guy, we've canceled out this guy. It has to be one of the tops too to calculate our delta G. Let me make some space here. This is kind of crazy. Okay, so you have your delta G, and the difference between this is, okay, they counted, they're doing divided by 1,000 because they're changing it from joules to kilojoules. They have the Faraday's constant, and they have my E. So this guy, and kilojoules. The only guy that we're wondering about is the N. Is the N 12 or 4? Those are the only. Is the N 12 or 4? What does the N stand for? It stands for moles, but not just any kind of moles. It's the moles of electrons. So, we have to flip this one. We have to flip this equation because it is the oxidation reaction. We leave this one on its own because it is the reduction reaction. So notice the electrons here. This has 3 and this has 4. They need to cancel out. How do they cancel out? We will multiply this top equation by 4. We will multiply this bottom equation by 3, and they will cancel out, yes? You'll have 12 electrons and 12 electrons. The correct answer is A, 12 electrons. Okay. Now, there's so much thinking that needs to go on in this question. Remember, so at the beginning, you have to realize that since we're trying to obtain electrical energy, this has to be a galvanic cell. If it's a galvanic cell, your E cell must be positive. If your E cell must be positive, then, okay, from there, you have to calculate the delta G, and the delta G is by this equation, negative NFE. The negative NFE, the number of moles, has to be where the moles of electrons cancel out. So there's a lot to do here, but it's a very doable problem. You just got to really be good with the concept. It'll come to you pretty quickly. All right, number 6, aluminum plus 3 this. Okay, so you have a negative and a positive E cell. According to the standard reduction potentials given above, what is the standard potential for a reaction represented below? Okay, let's see what happened. I have Ag here, but I have Al3 plus, I have it there. So what did they do? They flipped the top one. But what else did they do? Is that how you write flipped? Is it 2 P's? No. Okay. They flipped the top one and they multiplied the second one by 3. Okay. Now, I'm here to tell you that multiplying by 3 does nothing. It does nothing to E cell. I know it did something to delta. It does something to delta H. I know it does something to K. It does nothing to E cell. Okay. So here we go. If you flip this equation, okay, let me just do it. I don't like, okay. Look at what this Ag is doing here. The Ag is positive. Now it's becoming neutral. So that must mean it must be gaining electrons. It is gaining electrons. It's no longer positive. It is neutral. It must have more electrons now. And on the other end, the Al is becoming positive. So it must be losing electrons. Gaining electrons, losing electrons. If it's gaining electrons and losing electrons, okay, the rig happens at the cathode. The oxidation happens at the anode, okay? So E cell, again, is equal to E cat minus E anode. Don't change any of these. All us doing flipping this made us realize that it was the anode, okay? So the cathode is 0.80 minus negative 1.66. Don't make this positive. Don't change it. Even though it flipped, don't change that. Don't change this number. Okay, so E cat minus E an, okay, you're going to add those numbers together. Look, that's going to become 0.80 plus 1.66, right? That's the key, that this negative became positive. So your answer is going to become positive, first of all. Yes? Your answer is going to become positive, and it's going to be over 2. The answer is D. Okay? So a lot of kids get confused with E cell. E cell, this formula, E cell, is the reduction of the E cat and the reduction minus the reduction of E anode. So don't get confused there. A lot of kids end up trying to make this Hess law, and they try to multiply by 3 or something like that. Or if you did it as in terms of equilibrium K, you would like cube it. I mean, no, the E cells don't change. Okay, so here we go. The answer is D there. Let's go to number 7. All right, NH3. Ooh, this is so freaking good. All right, the synthesis of NH3 is represented by the equation above. Based on the equilibrium constant K and the delta H of the reaction given above, which of the following can best be used to justify that the reaction is thermodynamically favorable? Okay, well, how do we know that this is thermodynamically favorable? Okay, look. Remember your delta G is equal to negative RT ln K? Okay, delta G being equal to negative R, okay, Ratlink, okay, that right there, that right there, the negative RT is always going to be negative. This is always going to be negative. You can't, R is a negative number, T is a negative number, but the ln K, so you want delta G to be negative. So you're hoping that this ln K will be positive. Now, how do you get the log of K to be positive? Well, the log of K is a positive number when K is greater than 1, when you produce more products than reactants. The log of K is a negative number when K is less than 1. So what do we have this scenario? This is our K. That is a huge K. There's a ton of products, very little reactants, meaning that the K is way greater than 1. If the K is way greater than 1, right? If the K is greater than 1, then you are going to be thermodynamically favorable. Your delta G will be negative. So your K is greater than 1, your K is greater than 1. I don't know what this is talking about. This is not what this is not talking about, which is true. So your delta G is equal to negative RT ln K is greater than 0? No. You want your delta G to be not greater than 0. You want your delta G to be less than 0. You want it to be negative because your products over your reactants is way greater than 1. That's how they say way greater. They put 2 greater than sign. It's like greater than. So great. Make America great again. Okay, like so great, like greater than any other country has ever been great. Okay, number 8. The electric current of 1 ampere passing through an aqueous solution of nickel nitrate. How long will it take to plate out 1 mole of nickel metal, assuming 100% current efficiency? Okay, I don't like focusing on these type of questions. I'll do it for you guys, but it's not something that comes up a whole lot. I think I only do it like 2 times in this entire packet, maybe 3. But I actually, okay, let me show you. All right, you have nickel nitrate, right, wanting to become plated nickel. So what had to happen? Well, this thing had to gain 2 electrons, right? 2 electrons had to come out. So that's kind of like a hidden detail in all of this. All right. If you have 2 moles of electrons, 2 mole, okay, you can multiply that by a couple numbers to make this make sense. All right. Then 1 mole of electron comes into play on Faraday's constant, 96,500, right? Like, oh, sorry, I should write the units. That's coulombs. And 1 ampere, let me just let you know, an ampere is equal to coulombs per second. Okay, so we have 1 ampere meaning we have 1 ampere, which means we have 1 coulomb per second. So this is going to be 1 coulomb per 1 second. Okay. So kind of stoichiometry-wise, or at least dimensional analysis-wise, your moles of electrons cancel out, your coulombs cancel out, and you end up getting seconds. So you have 2 times this number. The correct answer, B. Now, this doesn't appear that much. Now, the key to this question was realizing that that nickel nitrate becoming nickel was going to require 2 electrons. That's the key to this question. But in terms of doing the question, it's not that tricky. It's really just a dimensional analysis problem. So I don't actually spend a lot of times. And if this one is like out there for you, I mean, don't worry about it. Like this is, like I said, I think this only comes up one more time or two more times in the packet. I feel like if you're just good at your units and stuff, you can do a question like 8. The key, but like I said, the hidden gem right here is realizing that nickel nitrate is going to have a nickel 2+. All right, number 9. Okay, you have this going on. 2 molecules of the amino acid, of the amino acid glycine joined through the formation of peptide bond as shown in the thermodynamic data for the reaction are listed in the following table. Based on the thermodynamic, which is true at 298 K. Okay, I was confused. Okay, I was confused. I saw, remember our delta G is equal to negative RTLN K? So it tells us that your delta G is positive. It is not thermodynamically favorable. If it is not thermodynamically favorable, then I got news for you. Your K is negative. Or sorry, your LNK is negative. How is your LNK negative? Because then that means your K is less than 1. So I was looking for K is less than 1. Oh. And I think the one that, and then so your K is less than 1, but it's not negative. It's not less than 0. So the correct answer is B. It's a fraction. There's more reactants than there is products. That's why your K is some kind of fraction. So if, look, and I want you to logically think through that. If you produce more reactants than products, if you're not producing products, you're not thermodynamically favorable. You are not spontaneous. You need help, okay? So here's a lot of so remember, your RT, your negative RT is always going to be negative. But this negative times this negative makes it positive, meaning it is not spontaneous, okay? That is just a fact. So if your K is less than 1, not less than 0, not a negative number, less than 1, you are going to be a non-spontaneous reaction. All right, number 10. Under which of the following temperature conditions is the reaction thermodynamically favorable? And I'm looking at this and I'm saying, what? If this is positive and this is negative, remember, you have your delta G is equal to delta H minus T delta S. If this number, if your delta H is always positive and this is always negative, well then you're going to have a positive minus a negative, and that will always be positive. This is never thermodynamically favorable. The answer is D. Doesn't matter what your temperature does. All right, number 11. Thermodynamics. Okay, here we have our delta S, here we have our delta H. The combustion of ethanol is represented by the equation above, and the standard entropy and the enthalpy changes for the reaction are provided. When the reactants are combined at 25 degrees Celsius, essentially no CO2 or H2O is produced in a few hours. Which of the diagrams above could best help explain the low yield? Look, this is thermodynamically favorable. We have a negative delta H, we have a positive delta S. That's a perfect scenario to have a spontaneous reaction. However, that doesn't mean it doesn't have a high activation energy. It might need a spark, okay? It might need something to get over that activation energy. It'll eventually happen. It'll just take a long time for it to happen. So for the reaction, now it's not saying that this is not spontaneous. It's just saying it's super, super slow. So the correct answer is diagram 2, because it represents a reaction with a high activation energy barrier for the molecules to overcome, even if it is thermodynamically favorable with delta G less than 0 or negative. Now some of you guys are going to say, wait, if you have to add a spark to it, then why how could this be thermodynamically favorable? Doesn't that mean it needed help? No. The spark made it happen quicker. It was going to happen on its own. It just was going to take a lot longer to do it. Okay, so there are certain reactions that just can't happen. Okay, this can happen. It just takes a long time. Okay, all right. Number 12. Methane, oxygen, carbon dioxide, water, delta H, delta S. The chemical equation above represents the exothermic reaction of CH4 with O2. Which of the following helps us explain why the reaction is thermodynamically favorable? Look at this thermodynamics here. This is a pretty cool question, actually. This is very AP-ish. Delta G is equal to delta H minus T delta S. So your delta H is negative 803. Your T is 2000. And your J is 0.005. What? How did I get that? Okay. This 0.5 right here is not kilojoules. Okay. Delta G and delta H, these are both in kilojoules all the time. This is kilojoules, this is kilojoules. So when this is in joules, you got to change that. Okay. So that's going to make that number super small. And I found out this is negative 803 minus, this ends up being 10, I believe. So the answer still ends up being 793. So I just calculated that just to make sure. My delta G does turn out to be negative. The reason why is your delta S is so freaking small, right? It's not enough to overcome the delta H. Now, this will actually overcome delta H at some crazy temperature. I know 2000 sounds like a lot, but you need a lot more when your S is that small, okay? But at some crazy temperature, like when you get really, really high, this will become spontaneous, okay? So, but let's try to find the correct answer. So the correct answer for number 12 is D. The amount of energy released when the product breaks bonds when the product bonds form is much greater than the amount of the energy needed to break the reactant bonds. In other words, this is super exothermic. Bonds broken. No, this is what? The amount of energy released when the product bonds form is much greater than the amount of the energy needed to break the reactant bonds. Yeah. Bonds broken minus bonds formed. Yeah. So you have way more bonds broken. You have way more bonds formed. You have way more bonds formed than you do bonds reactant. So this is so exothermic that the delta S cannot overcome it. Okay, the answer is D. Okay, number 13. Okay, in a blast furnace, the reaction represented above producing Fe from its ore, iron oxide. The reaction is thermodynamically favorable and based on a coupling of two reactions represented below. Which of the following identifies a limitation in how the representations above describe a system of coupled reactions? Okay, I'll be honest, I didn't really know what these words were saying. I was like, what the heck is the limitation in how the representation, like, what's the limitation? So, what? The answer here is C, and I'm just going to leave it at that. I don't know why. Okay, I was like, why would you need the delta? Just because we need to know if it's thermodynamically favorable? Like, if they gave us the delta G, then we know it's thermodynamic. I think this question is so simple. It's just asking, how do you know something is thermodynamically favorable? And you're like, well, I have to know the delta G's. You know, I mean, it's almost so simple. Like, I can't figure it out, right? Like, what am I supposed to do with these? Like, there's nothing. I don't know what I'm supposed to show you how to do that. Maybe I'm just supposed to tell you the definition of delta G is the thermodynamic favorability. That's what I'm going to assume. All right, number 14. Cu, Ag, equilibrium constant for the reaction. Okay. Which of the following correctly describes the standard voltage and the standard... okay. Wow, this is such a cool question. Okay, so first of all, they give you a K, right? They gave you the equilibrium constant, K. Okay, so for you to get that, you get delta G is equal to negative RT ln K. Now, What is the K? It's this huge number. It's a gigantic number, meaning it's super positive. This means K is way greater than 1. If K is way greater than 1, ln K is a positive number. T, temperature, is always positive. R is always 8.31. This is positive, positive, positive times a negative. Positive, positive, positive times a negative is overall a negative number. That means your delta G is a negative number. If your delta G is a negative number, you are spontaneous. Okay, so this is guaranteed. Okay, so what does that say about your E? Well, your delta G is negative. Okay, so your delta G is negative, and we can translate to our NFE. All right, N is always positive because that's moles of electrons. That can't be negative. F is always positive because that's Faraday's constant. So if you have a negative delta G is equal to a negative positive number times a positive number, E better be a positive number. Oh, shoot. Okay, because then you have a negative times a positive, positive, positive is equal to a negative. Okay? So E cell must be positive. All right, so... All right, this is still in the run. Okay, this is E is not negative. They're not negative, and they are not both 0. So E is positive. Now is G positive? No. G is spontaneous. It is negative. So E is positive, G is negative. The correct answer is A. C, get the heck out of here. You don't know nothing. All right, answer is A. Notice this is one of those questions I was talking about when you're going to have like one form of your delta G cross over into another form of your delta G. It just causes a lot of nasty work. It's kind of amazing. All right, let's do number 15. According to the half reactions represented above, which of the following occurs in an aqueous solution under standard conditions? Okay, it's saying this thing occurs under standard conditions, means it's occurring spontaneously. It's happening under, it's occurring. The word occurs means it's spontaneous. So you're either going to have this situation. Okay, remember you have your E cell is equal to your E cat minus your E anode, right? So you're going to have one of two situations. You're either going to have 0.34 minus negative 0.41, or you're going to have minus 0.41 minus 0.34. Now, I hope you can see that this top one is where your E cell is positive, okay? This is when your E cell is positive. So this must be the answer. Your E cell must be positive for your delta G to be negative, okay? When E cell is positive, right? Delta G is negative. That's the situation you want. So this is wrong, okay? Why? Because that would provide you a negative E cell. If you have a negative E cell, then you have a positive delta G. Remember, we are also looking at this in terms of delta G is equal to a negative NFE. Okay? So you want your E cell to be positive here. If you want your E cell to be positive, you got to choose the top one. Okay? So here's our winner. So what does that mean? So this is our cat, and this is our ox. Oh, sorry, not our red. No. It is our, I chose everything except for the right one. It is our anode, okay? Our cathode and our anode, okay? Now, a cathode is where reduction occurs. An anode is where our oiling occurs, okay? What is the top one showing? It's showing copper gaining an electron. Yeah? So, good, because cathode, red, rig, yes? Reduction is gain, okay? But the second one is showing chromium? Chromium gaining an electron too. That's not right, because that's the anode. It's supposed to be losing the electron, meaning the electron should be a product. This should be oiling. So what do we got to do to this one? We have to flip it. Flip it, please. All right, when you flip it, so we should have Cu2 plus on the left side. That's good. We should have Cr3 plus on the right side. Oh, that's good. That's the only one. Okay. So the correct answer is B. But notice what you will have to do to the CR. You have to multiply it by 2. Why? This is super messy. Let me make it a little bit clearer. Why do I have to multiply CR by 2? Because the electrons won't cancel out. You need this guy to cancel out with this guy. So notice that there are no electrons written left in here because they canceled out. So you have to have both the CR3 plus and the CR2 plus have to be 2's here. Okay? So that is the correct answer is B. All right?